Spectroscopy is the measurement of a light spectrum, and we use it for a variety of different purposes. We're starting with IR, where we use it to determine the functional group that is in a molecule, but we can also use it for reaction monitoring or to match unknown compounds to known compounds. The chemist's sort of best friend, or the organic chemist's best friend, is the NMR, nuclear magnetic resonance, and we'll get to that soon. You can actually figure out the full structure of a molecule using NMR. We'll also look at mass spec and UV vis. So the big idea of spectroscopy is that you take a system that's lower in energy and you shine light on it, and it absorbs light that has the energy equal to the difference in energy between the two energy levels here. And so this is the idea of a quantized system where the system can have energy of E1 and energy of E2, but not anything in between. And so you can shine light on it. And if that light is exactly equal to delta E as shown here, whatever the system is will move up to E2. As a result of that absorption of energy, you end up with a higher energy system, and then eventually it will just go back to the ground state. You've probably seen this before in atomic spectroscopy. This is UV vis, where it's in the UV light where you go from a lower energy molecular orbital to a higher energy molecular orbital. That's actually molecular orbital spectroscopy, UV vis. It works for atomic spectroscopy as well. So IR in particular is not looking at energy levels like the shells of an atom or a molecular orbital. Instead, we're actually looking at differences of energy of vibrational states. And so what I mean by that is, let me move this around, try to get it into the frame so you can see it. That didn't work. Let's try that again. I'll get there. Where is it? There we go. All right, we're getting close. There we go. All right, so molecules, this is meant to be water, are always moving. And of course, there's rotation, which we've already talked about, but they are also vibrating. And so here's a couple of different types of vibration: the symmetric stretch, an asymmetric stretch in the middle, and then a bending mode of vibration. So if we go up here, let me find it. Alrighty. So if we look at a vibration, we can see that here are two atoms, the bond's vibrating between them. You can see it's kind of moving in and out, and it's going to about, bond length is about here. This is the maximum bond length as that bond vibrates. So if we have, or if we apply light and it's absorbed, in other words, it equals that energy difference between the two energy levels, now we can see that bond is excited. It's going to vibrate. Its vibration is going to change and be higher in energy. So eventually heat gets released and the molecule moves back to the ground state. This is why things that when you shine IR light on them, they get warm. Is that when the molecules move from the higher energy molecular state to back to the ground state, as shown in the second step over here, that releases heat. So the IR part of the electromagnetic spectrum is it's lower in energy than visible light. You can see there. And of course, there's a range of wavelengths within that range that we call the infrared part of the electromagnetic spectrum. And so, so this is what an IR spectrum looks like. And along the bottom is a measurement. Let's go back to that electromagnetic spectrum here. We're looking at this area here, but we often talk about wavelength and in nanometers. And that's how we measure different energies of light, is of the wavelength of the wave. But in IR, we kind of use these weird units. Instead of a wavelength in meters or nanometers, we use wave number. And wave number is actually inverse centimeters, so it's centimeters over 1. And it is proportional to frequency. So as the wave number goes up, frequency also goes up, energy also goes up. So that's the units. It's just something whenever you see a wave number, think you're looking at IR. The other thing to notice is that that we're actually measuring transmittance on the left side here. And so each of these things going down is a band. And when it's way down, and this is weird because we're usually used to looking at peaks which go up, but these actually, it's like they're upside down. And so if you have something that has like a 5% or 10% transmittance, like this band right here, what that means is that most of the light has been absorbed. And so it's being absorbed by the molecule as it goes from one vibrational state to another. And this is just one molecule here, and you can see that it absorbs in lots of different places. And that's because every molecule has lots of different vibrational states. So it's going to have a bunch of different bends, and it's going to have a bunch of different stretches. And the more complicated the molecule is, the more of those it will have. And so you can see in this case that this molecule has it just has a whole bunch of these bands or absorbances, as you can see. So as far as the part of the IR that we actually look at, we usually just look at this part on the left where the wave number is higher than 1500. And so this is the part that tells you what functional groups you have in the molecule. And what we'll see in the next clip or next little video is which functional groups are indicated by which wavelength, and or which wave number. And just to kind of give you a heads up on that, this big band over here to the left at about 3500, or with the max at 3500, is an OH, an alcohol. We have this thing at 3000, which is a bunch of CH bonds. And then over here at about 1700, that's a carbonyl. So you'll get used to kind of reading that. I can't tell anything more really about the molecule than that it has a carbonyl and an OH group in it. But still, that's some information. This fingerprint region here is indicative of a particular molecule. So if I found a spectrum of a known molecule with the same fingerprint region, I could identify my molecule. It would be the same thing.